category of reaction is called a double replacement. In a double replacement, there will be two elements replacing each other in compounds. So for example, look at this first reaction. Sodium sulfide reacting with copper chloride. Now check the product side. Copper is now with sulfur and sodium is with chlorine. There was a double replacement. The sodium has bonded to chlorine and the copper is with sulfur. Double replacements will involve two compounds. That's kind of the main difference between a single replacement and a double replacement. In a single replacement, there is a single element switching spots with an element in a compound. In a double replacement, there will be two compounds, and each will have an element switching spots or replacing each other. My second reaction, I have potassium iodide reacting with lead nitrate. Well, all the ions are still there on the product side, they're just rearranged. Now I have potassium with nitrate and lead with iodide. A double replacement. What do you know? Now, of course, there's got to be some exceptions that sometimes these double replacements don't work. So the rule. In order for a double replacement to work, both reactants must be aqueous. Okay, so aqueous means that they're in solution. Here's what happens when something is in solution. Let's say I have sodium chloride, NaCl aqueous. When you dissolve sodium chloride in water, it's a physical change. All that happens is that the ions separate from each other. We're going to talk a lot more about solutions fourth quarter, but you'd have something that kind of looks like this. Sodium ions and chlorine ions. The ions just let go. They dissociate or separate. Now, if you evaporate the water, then the sodium ion is attracted to the chlorine ion and it shifts back to the original solid. But when something is aqueous in solution, all that happens is that the ions separate from each other. Well, here's the deal. If I have this first reaction and I want to have a replacement in both compounds, then they need to let go of their current partner. In order for copper to come in and potentially bond with sulfur, sodium needs to let go of sulfur, copper needs to let go of chlorine. They need to dissociate or separate from their original partner. They need to be aqueous. If one of your reactants is not aqueous, it means that they will not separate from each other. The ions will not let go. They're together forever. Well, if the ions don't let go, then you can't make a new product. You can't have a replacement. So that's the only rule of a double replacement. You need to make sure that your reactants will dissolve in water first. They need to be aqueous. And so here's this magical chart that I've been talking about. It's called the Solubility Chart. You can use this chart to predict phases for a lot of compounds. Now, anything that we'll run into is on this chart. Obviously, it's not going to include every possible compound, but it's good enough. The chart has two halves. On the top half, compounds containing these ions are soluble in water. Soluble in water means aqueous. So, for example, anything with ammonium, potassium, sodium, chlorate, nitrate, anything with those ions will be aqueous in water. They will all dissolve in water. Most acetates, chlorides, sulfates will also dissolve in water unless bonded with these ions, which will make them insoluble. Insoluble means solid. So for example, sodium chloride is aqueous without any exceptions. If I have water present, salt dissolves. Sodium compounds are all aqueous with no exceptions. Most chlorides are aqueous. There are a few that don't dissolve, but sodium's not one of them. Now you might have something then like silver chloride. Silver chloride is a solid that will not dissolve in water. So you could not do a double replacement with silver chloride as one of your reactants. The silver and the chlorine won't let go. Most sulfates are aqueous. We use a lot of copper sulfate in the lab. It's a really pretty blue solution. It's aqueous. But calcium sulfate is not. Calcium, barium, lead, strontium, and mercury sulfate will not dissolve. On the bottom half of this chart, it says compounds containing these ions are insoluble in water. So these ions are typically not soluble. They're solids. Unless bonded with these ions, which does make them soluble or aqueous. So for example, most carbonates, hydroxides, oxides, phosphates, most of them do not dissolve in water. They would be solids. But then look at the exceptions. It's a lot of potassium, sodium, ammonium, which if I check on the upper half, those guys are aqueous with anything. You will never need to memorize either the reactivity series for single replacements or the solubility chart for doubles. I will always, always, always give you these charts. So here's how it works. Write the reaction between barium nitrate and potassium sulfate. Now maybe you're good enough, eventually, that you can pick this out of a hat as being a double replacement, because double replacements are often two compounds. Barium nitrate, barium is a +2 ion. Nitrate is -1. So I need 2 nitrates. And then I have potassium with sulfate. Potassium is +1. Sulfate is -2. Now here's the other nice thing about the solubility chart. These polyatomics are right there. And like here's nitrate and sulfate. If you forget their formulas and charges, they're staring at you. We're going to need 2 potassium to make that neutral. So when I recognize at this point that it's 2 compounds, that's your double replacement. We need to make sure that both reactants will dissolve in water. There's no barium on this chart, but there is nitrate. Nitrates are soluble in water with no exceptions. So barium nitrate is aqueous. Yes, it will dissolve in water. Potassium, soluble in water with no exceptions. Aqueous. Or you could look up sulfate. Sulfates are aqueous. There are a few that don't dissolve, but potassium is not one of the exceptions. Okay, so this is going to work. We can dissolve our reactants in water, which means that they're willing to let go of their current partner and maybe take on a new partner. So kind of like the single replacements, we're going to switch like-charged ions. I often switch positive for positive, but there's no reason that you couldn't switch like nitrate and sulfate. That'd be fine. I don't know, I usually just switch the positives for no other reason, but they come first. So let's flip them. I'm going to have potassium with nitrate, and then barium with sulfate. And like any other replacement, when we make a new combination of ions, we have to check their charges. So potassium was +1, sulfate, or I should say nitrate, -1, neutral, yes. Ooh, I like this. So the barium is +2, sulfate is -2. Neutral, yes. So balancing this is a piece of cake. I got 1 barium, I need 2 nitrate, I need 2 potassium anyways, 1 sulfate, done. The last thing we should do is get the phase symbols for our products. So you can use this solubility chart to find any phase symbol of a compound. It doesn't have to be a double replacement. You can use this for a single replacement or a synthesis or something like that. You just have to use it for double replacements to check your reactants. But we can find these phases of the products. Anything with potassium is soluble in water. Same gig with the nitrate. This potassium nitrate is a solution. Now most sulfates are soluble. There are some exceptions. And gosh darn it, barium is one of them. The barium sulfate is a solid precipitate. It's a solid that will be formed from the reaction of 2 solutions. So if I really run this reaction, I'm expecting some kind of a cloudy solid. If I let this solution sit for a while, the cloudy solid will sink to the bottom, and the remaining liquid on top would be my potassium nitrate solution. Or if I filtered, the barium sulfate precipitate would be collected on my filter paper. The potassium nitrate solution would drip through into my flask, which is totally what we're doing in one of the next labs. It is fine to produce a solid in a double replacement. It's very common. It's just your reactants that must be aqueous. Okay, so let's try one more. Copper to chloride. Copper to chloride. That's 1. I'm going to need 2 chlorine. And magnesium phosphate. Magnesium ions are +2. Phosphate is -3. Yikes. So let's make this neutral with a +6, -6. Double replacement, I have 2 compounds. They need to dissolve in water. And so you probably don't find copper. No copper. But I do see chlorine. Chlorides are soluble in water. There are a few exceptions. But copper's not one of them. So far, so good. Copper chloride dissolves in water. Magnesium phosphate. Well, here's phosphate. Phosphates are insoluble in water. There are a few exceptions, but magnesium is not one of them. Magnesium phosphate is a solid. And this then would be a no reaction. Nothing happens. Both reactants must dissolve in water. If magnesium and phosphate won't let go, then the calcium and chlorine ions are like, what are we going to do? We don't have anything new to bond with. That's your no reaction. We are totally going to run a bunch of these in the lab. And you'll see that sometimes they work. And you'll see, oh yeah, it's cloudy. I'm getting this little solid formed. Sometimes they don't work. And we can predict that by using this solubility chart for double replacement reactions.